How's that? Sounds okay? I hate it. I told them. It's impossible, especially if I'm typing. Yeah. Unless I type with one hand. And I've tried that and it just doesn't do it. All right, that's the bell. It's about time for us to begin. Oh, I'll tell you, they're getting late. So let's get started, shall we? Welcome to week 3 of this GPU series. Today's class is one where we really get cranking with this lecture series. Week 1 and week 2 were pretty much introductions to the art of numerical analysis and using computers to help us with engineering work. Today we actually start to look at GPU devices. And so today I'm not just going to look at GPU hardware, but we're also going to start allocating memory on the GPU device, which is actually going to be really interesting for everyone here. So let's get cracking. Hope you guys enjoyed your holiday. Obviously this is not week 3, this is week 4, but this is the 3rd lecture in the series. So let's continue. So being Taiwan, a lot of people aren't that familiar with what a GPU is. I'm guessing most of you guys are because you're here. But if you go ask your little sister what a GPU is, maybe she won't know, or maybe your family doesn't know, because a lot of people nowadays play games on their tablets or on their mobile phones and they don't require the computing power that comes with a GPU. But for a while there was a period of time where we actually needed GPUs to do something very special for us, and that was for playing games. Now, computer games have changed a lot in the last 10, 15 years. This is a screenshot from 1 or 2 very important games. Anyone here know what games these are? Counter-Strike is on the right-hand side and Half-Life is on the left-hand side. Yeah, these are basically the same game. Counter-Strike is a mod for Half-Life. Can anyone tell me what year Half-Life was released? 98. So Half-Life and Counter-Strike were released in my first year of uni, as a matter of fact. And I still passed. Look at that. Can you believe it? Actually, I was not that into computer games until my final year when someone introduced this to me. But have a look at the quality of the graphics. Half-Life was one of the special ones because it was, at the time, 1998, this is the first-person shooter, one of the first ones to use true 3D engines to help accelerate. Before Counter-Strike and before Half-Life, there were other games like Doom and Quake, and even earlier first-person shooters. They all employed three-dimensional components to a degree, but they never went so far as Half-Life did. So Half-Life was one of the first hardware-accelerated three-dimensional shooters. About that time, we started to realize, because when people bought Half-Life, most people who were using computers to play games at the time, they had maybe a Pentium, probably a Pentium 1 at that stage, not even a Pentium 2, Pentium 1, the first Pentium that was released. Not many of these computers had graphics cards. Most of the time people were using these Pentium single cores, Pentium 1, to drive their computers, and those CPUs were also responsible for accelerating the graphics. So in this case, when we're playing Half-Life or Counter-Strike, the CPU is doing all of the work. CPU is doing the computations for the targeting and also doing the 3D graphics calculations. Now, before 1998, before Half-Life came along, this was fine. There weren't that many games that required that much power, but with Half-Life in particular in 1998, people saw a need for hardware acceleration of graphics. So it was about that time that companies and NVIDIA and Intel started to think hard about making discrete graphics affordable for the greater consumer community. This is computer gaming back then. This is computer gaming now. I'm afraid you can't see very well on the screen that is here, but all of these slides are available online. Can anyone tell me what these 2 games are? This will require a bit of commitment. Huh? Witcher is on the left, Witcher 3, great game. I wasted a lot of my life on that game. And on the right-hand side, I own this game, but I've never played it because it's too scary. It's Alien Isolation. And it's terrifying. And if you have a look at the notes online, you'll see screenshots from this. the screenshot of Alien Isolation, that's not an artificial image, that's a screenshot taken from gameplay. It is terrifying. The computational complexity of both of these games is much, much stronger, much higher than Half-Life, the original Half-Life game. Most of you are still waiting for Half-Life 3 to come out. I think you'll be waiting a while. I don't think they're going to release Half-Life 3, I'm pretty sure. But in the meantime, you've got fun with Geralt and all of the Witcher team that you can muck around in, and you've got that alien who can kill you a million times. The computational power required to play those games goes far, far beyond what a CPU is capable of doing. Nowadays, if anyone will tell you, if you want to play Witcher 3, you're going to need a GPU. If you have a computer without a GPU, or what we call an integrated GPU on the chip, which is what most Intel chips come with nowadays, you might be able to play Witcher 3 on the lowest resolution, on the lowest detail setting, on the slowest way possible. But if you want to play it with any kind of speed the way it was designed to be played, you need a GPU. And that is the way most of the world works nowadays. And due to this increase in graphics complexity in games, the computational power of the GPU is increased at an astonishing rate. Here we have a graph that shows us the theoretical peak performance of some of the GPUs that we're familiar with. Starting from the year 2000, so this is actually coming up on the year Half-Life 2 was released. Half-Life 2 I think was 2002. I could be mistaken about that, around that time. I know that Half-Life 2 was released around the same time the world's first discrete GPU, affordable discrete GPU was on the market. Yeah. I'm counting them. Those were 98. So they came after Half-Life 1, around the same time. But I don't want to talk too much about those. They disappeared pretty quick. Here we see the GeForce series. My very first GPU was actually a GeForce FX right there, 5800, when I was in Taiwan. I was living in Taiwan when I bought that device actually. It was pretty cool. But you can see since that time, the power of these devices has increased at an astonishing rate. You can see there's a strong difference between single precision and double precision. So the desire to perform single precision computations in engineering is very strong. A lot of computations require double precision, but nowadays we're trying to find more and more ways to modify the algorithms to allow us to perform the same computation with the same correct result in single precision to allow us to get more juice out of these devices. But if you have a look at these trends here, you can see the rate at which GPUs are increasing, and you can also see the rate at which CPUs are increasing in behavior, in complexity and compute power. CPUs are also getting faster, not at the same rate that GPU devices are. So here we are. Of course, we're in 2017 now, so there are some minor changes to this graph, but things continue to grow. And so when is the right time to get into GPU computing? Well, anytime you can. It would have been better if you started off 10 years ago, but here we are, and we can safely assume that this chart is going to continue to increase, and the computational complexity and power of these GPU devices are going to increase as well. But where did it all begin? Back in the days, like I said, when I was in university and when you guys were in preschool, I'm getting old here, computers didn't have a place where you could stick a GPU because consumer GPUs weren't available. But around the time I started university, manufacturers started creating motherboards which were able to accept these consumer products, which were able to allow us to accelerate these graphics computations. The very first series of motherboards, or sorry, I would say the first easily accessible consumer product which allowed us to place a dedicated GPU in a computer, was the AGP port. So if you have a look here on a motherboard, this is an old motherboard. You can see there's a VIA chip. Back in the day, VIA were kings, man. They were big. And they are still big, just not as big as they were. VIA is in Shinju, right? If you guys have a chance to go up there, you can see their company. There's the AGP port, the top one, the grey one. You've got the AGP on the top, and you've got these two legacy PCI slots here. These are not PCI Expresses, these are old school PCI slots. PCI slots are ways for us to put in devices such as network cards. Back in the day, I had a network card that plugged into one of those, and other things, RAID cards, other peripheral devices which allow your computers to perform with greater functionality. But that grey port there, that is the accelerated graphics port. That's where you stuck your GPU back in the day. So my first computer that I bought when I came to Taiwan the first time, back in 2002, had one of those AGP ports inside. And there is an NVIDIA GeForce Quadro card designed for AGP. There are several things that you should know about this card. You don't see the fan on there because the fan has been removed. But one other thing you should pay attention to is there are no slots, no plugs for power. The power was drawn through the motherboard. Most GPUs are able to draw power through the motherboard, through the slot which it is placed. This is an AGP slot. It's allowed to basically draw about 50 watts of power through the computer's motherboard. Before you needed more power, but back in the day, back when we were using this style of putting devices into your motherboard, we didn't need any more power than that because there weren't any GPUs powerful enough to require that much power. But that obviously changed very quickly, and nowadays if you buy a GPU from down the road, maybe a GTX 1060, you're required to plug in those power cables into your GPU. The GPU draws too much power to safely draw through your motherboard, so you need to have cables going directly from your power supply to your GPU. Oh, that is the old NVIDIA. And where was that made? You can see it was made in Taiwan. TSMC in Taiwan still continue to manufacture new GPU chips for NVIDIA and for many of the companies. So they have a whole team dedicated to all that stuff. Very interesting to work with. And how did it work? The GPU just plugged straight into that slot and sat at the back. So most of you guys should be pretty familiar with this. I'm only showing you on the odd chance that none of you have seen a computer with a GPU in there before. I know some people may not have, especially with the rise in popularity of those tablets nowadays, but that's what a GPU would look like going into the AGP slot. So there it is. You can see there is a fan on one of those GPUs, on another one there isn't. Back in the day, not every GPU had a fan on it because it just didn't draw enough power to warrant the heat exchange required to keep it cool back in the day. And you can see inside your slot there are many different contact sections for data and power to be transferred to and from the device. So the GPU was basically a standalone system, standalone piece of hardware that drew power through the motherboard directly and received data from the CPU's memory and from the CPU itself through those slots onto memory that was kept on the GPU device. We can also see here I've written here that the maximum power is about 500. Typical GPUs now, good GPUs will draw around 200 watts of power. If you really want to go crazy and go get some GPUs which are about 5 years old, you can find GPUs which draw 500 watts of power. But since, well, most recent changes to NVIDIA's architectures have been focusing on low power, most GPUs now only draw a maximum of 200, 250 watts, depending on the GPU that we're talking about here. So we can see here, the GPU is a standalone device. It is its own machine. It has its own memory, its own CPU system, its own scheduling system, its own cache system, its own memory. It requires power to be provided through the slot it sits in. Modern GPUs now also have additional power coming from the power supply unit. And what does all of this essentially mean for us? The GPU should not be treated as part of the computer that you're programming on. When we program GPU devices, we do not program them in the same way as we program regular applications. There are several things we need to consider. The GPU device has its own memory. The CPU cannot access or control the memory on the GPU easily. The GPU has its own CPU units. Those CPU units cannot access or control memory on the CPU on the host at all. These are separate devices and they are connected through the slot in which they sit in. In this case I just showed you AGP, but we don't use that anymore. We use PCIe, which I'm going to show you in just a little bit. But we need to start thinking about this right now. The codes that we've been writing up until this point have just been your ordinary methods where we allocate memory in the normal way into memory on the host, and we use printf to display our messages, and we perform calculations in one way, but none of those codes are going to be acceptable in any way, shape or form to run on the GPU because it is a different device with different memory in a different physical location. Let's continue. Oh, PCIe. AGP didn't last long. So, I can't remember when my AGP motherboard was already out of date and we had to replace it with PCIe. But PCIe came along. PCIe is never a standalone argument. We can always say that every motherboard that comes with PCIe has different lane lengths. So most motherboards come with a variety of PCIe slots in them. Here's a picture of a Z87 Pro motherboard and a ASUS one. We can see here that there are actually a couple of PCIe 16 slots. There are a couple of shorter ones too, but all of the yellow ones you see here, and one of the grey ones that you can't see very well on this screen, are all PCIe slots. But they all have different lengths, so let's have a look at each one. Come on, computer. There we are. This is a better picture. So, on the top, we have a PCIe times 4. That basically means there are 4 PCIe lanes available for that device to use for communication of data to and from the motherboard. The number of lanes is basically a guide for us to know how much bandwidth a device can use for transferring memory from a device sitting in that slot to the motherboard. PCIe times 4, that's a cute little thing. Okay for slower network cards, maybe Ethernet cards, like 100 or 1000 gig, but, or Mbps, sorry, 1 gig. But if you want something bigger than that, if you want to have the capacity to transfer data to and from your device in this slot faster, then we need a longer length port, and those longer ones are the PCIe times 16s. So PCIe times 16 is basically where you plug in your GPU nowadays. It doesn't matter where you get your computer. You can go to the shops at this train station, or you go to Kaohsiung, Zhengguolu. Is there even still a Nova in Taipei? Anyone here from Taipei? Yeah, Yiqian's Taipei main station. There used to be a big building, a Nova building that used to sell computer parts. I remember when I first came. Huh? It's still, I can't believe it. Anyway, you can go there. You can buy this motherboard from a supercomputing vendor or from a shop down the road. They're all going to have the same PCIe slots on them. So there's very little difference between the PCIe slots on a supercomputing motherboard or on a regular motherboard. What does matter is that the number of lanes available for access to those slots through the CPU's North Bridge will depend on which CPU you get. So Xeon cores have a larger capacity in their North Bridge to enable communications between the CPU itself and the device inside this PCIe slot. What do you guys really need to know? If you're going to plug in a GPU, plug it into the PCIe times 16 slot. That's basically all you need to know. I'm not going to spoon feed you too much about this. We will have a chance to build a GPU system later in the semester. Here is a typical GPU device with a fan removed. That's your GTX 1060. Why do I show this one? Because it gives you acceptable performance and you guys can probably afford it. It's not that expensive nowadays if you want to go grab one. It's not a bad device. Of course, it's stripped of a lot of things here, but let's have a closer look at the 1060. On the left-hand side there, you can see I've highlighted different sections. The actual core itself, the collection of streaming processors which makes up a GPU core is highlighted there in the center. All around the outsides are the memory for that device. You've got power controllers on the left. You've also got other controllers and other things which go onto that board. The chip that TSMC makes is the GPU core in the middle, and different vendors make the different other things around the outsides, and different vendors also make the boards. So that's why you can go buy an ASUS or an MSI or a gigabit GPU device. They all have the same chip, but they're going to have different boards, different memories, different controllers on them. So that's what it is. So you can see here straight away, this core here, it's very separate from the system which it sits in. It has its own memory. Let's have a look at how this plugs in. There's an animation there that I'm just going to skip past. Most modern CPUs have North bridges built in. North bridge is a part of a computer system which allows communications between the CPU and any peripheral devices. In this case, the GPUs sitting inside our PCIe lanes are peripheral devices. North bridge controls those, and the North bridge is inside the core. Once upon a time, you actually needed to buy a motherboard that had a separate North bridge. You can still see the South bridge here. South bridge is this part. When you buy a new motherboard, the difference between all these motherboards that you buy is the South bridge nowadays. Back in the day, you'd buy different motherboards and you'd get different North bridges, different South bridges. Now all the North bridges that enable communications between, North bridge enables communications between PCIe and SATA and memory. Oh, sorry, not SATA, just PCIe and memory, my apologies. South bridge manages SATA. Nowadays, when you buy different motherboards, you get different South bridges, which means you get different performances on SATA and USB. which you can see here. Now, communications between our GPU go from the core, its north bridge inside the core, to the PCIe slot, then to the memory controllers which allow access to the memory. What is the moral of the story? If you want to perform calculations on GPUs, you can't just write a code and start computing stuff on that memory. First of all, there are two things we need to do. One, we need to transfer that memory to the GPU device. That's going to require a special function because the CPU itself can't touch the memory on the GPU. Then we need to find a way to issue instructions to the GPU controllers and the cores to perform computations upon that memory. Then when our computation's finished, we need to grab that data from the memory in the GPU and ship it back to the CPU. So there are actually three phases there of computations that we need to do, three steps. One, we need to allocate memory and copy the memory across first. Then we need to perform our computations, and then we need to get the information back. There are mechanisms available to us now that allow us to do this automatically. I trust them about as much as I trust my wife with a credit card on shopping day. Basically, that's what I'm trying to say here. That's exactly right. I didn't say that though, you said that. So that I can use this loophole to escape. But I don't trust the automatic stuff. In this course, we're going to do all of this manually, and we're going to start today. So, operations on the GPU are not as simple as you might imagine. We're going to be completely hands-on and completely manual, and we're going to do every step properly. There is another complication for us that you guys might be familiar with. There was a computer game released in the 80s called I Have No Mouth But I Must Scream. It's actually made from a book. Have you guys heard of this book? I Have No Mouth and I Must Scream. Google it. If there is an error on the CPU, if you've written a code and it's running and there is a problem, it will return to you an error. It might give you a message saying there's a segmentation fault or something. The CPU has a mouth and it screams all the time. The GPU, if something happens on the GPU while it's computing, it's not the same as a computer, it's a separate machine, it has no way of telling you. So something can go horribly wrong, but there's no way you will know because it can't tell you, because you can't print F from the GPU, it can't print messages to a screen, it can't talk to you, it can't tell you anything. You can have your GPU doing complete rubbish and you'll never know until you check your result. Luckily for us, we're engineers, so when we see our result, we normally know if it's rubbish or not. But this is a strong assumption, so we're going to work on that. Come on, computer. The CPUs inside the GPU itself are also not a trivial thing to think about. These GPUs are designed for one thing, I've already told you that, gaming. These GPUs are designed to accelerate graphical computations. GPUs are not designed to perform high-performance computing calculations. The engineers at NVIDIA do not make computing cards. I'm going to get in trouble for saying this. The engineers at NVIDIA make gaming cards, and then they stick stickers on them to have you believe that they perform computations. And more recent computing cards produced by NVIDIA are in fact quite substantially different to their gaming GPUs, but this is more or less a recent development. When we first started doing GPU computing, we were basically taking gaming cards and using them for compute. And most of us still do this. Now, the actual cores themselves, I'm serious when I tell you, the CPU cores themselves inside the CPU devices are very similar for both the computing cards and the gaming cards. So we still need to consider this. What is going on with this machine here? It is flashing like it's Christmas. So, when we render 3D graphics computations, what do we do? Well, we have a three-dimensional scene. I'm not going to show you pictures of this, I'll describe it. We have a three-dimensional scene. We have a fixed resolution for our monitor. Might be HD, that's what? How many millions? 2 million pixels on the screen at once? Is that about right for HD? Each pixel we need to perform a depth computation and some shader computations. The key is, for any given 3D scene, the actual computations performed for each pixel are identical, but we assign a different streaming processor to each of these pixels for our computation. So we have 2 million pixels. If we're going to perform computations for 2 million pixels on your display, we're going to need a very large number of cores. The GTX 2060 has 1,280 streaming processors. So that means each streaming processor will take on about 2,000 pixels. And it will perform computations for those pixels to help accelerate that computation. The key is that each of these processors, performs an identical computation. The only thing that changes is that because each pixel represents a different spot in 3D space, the data that we perform our computations on differs. But the nature of the computation performed by each core is identical. What does this essentially really mean? When we write functions for the GPU, we cannot write two functions and say one half of all of these streaming processors do this function, the other half do this function. The GPU is designed to do one thing, render graphics for computer gaming. It is up to us to come up with single functions which trick it into believing it is doing that, but it is not that simple. The key is for us to remember that all of these streaming processors will be working on the same single function that we write. They can have access to different data points, that's fine, but these different data points will have the same function performed upon them. If you ask different streaming processors, different shader processors on this device to do different jobs, this is something the GPU was not designed to do. GPU is designed to play games, do graphics computations. It is very good at this. The further away you go from this kind of computation, the harder it gets for the GPU to do. The largest challenge, if you have different types of computations going on in these different shader processors, is load balancing. And we'll talk about that a little bit later on. Of course, it's not that simple. We can see here on this GTX 1060, there are a large number of streaming processors, or shader processors, SPs, but they're not sitting individually. They're very, very different to the cores that are on your i5 or i7. Your i5, i7 are complex cores that come complete with their own cache, their own different levels of cache, their own controllers, many, many different things. But these streaming processors are grouped together in larger groups. Oh, yeah. What I just described before, where we perform large numbers of computations in parallel across different data but using the same computational technique or function, that's called SIMD, where we perform single instructions across multiple data. That's what the GPU is designed to do. The current models of Intel CPUs have been designed over the years to excel in MIMD computations. That's multiple instructions across multiple data sets. That's basically what the i7s and the i5s have been designed to do. Hence there is a very strong difference between writing code for a GPU and writing code for a CPU. CPU, we want to perform the same computations across many data points, and this is the only time the GPU will succeed. It will perform quickly. Yes, the SPs are not standalone. You can see in this picture here, they're grouped together into teams. These groups, depending on which generation of GPU you're looking at, I still like to call them SMPs. SMPs were the term that they were used, or that we used to describe these things back when the first computing GPUs were released in CUDA version 1.0, or with the Tesla series. But nowadays they've been called many, many things, SMXs, SMs. I'm going to refer to them as SMPs. Still, streaming multiprocessors. All you basically have to remember is that these are groups of streaming processors or shading processors stuck together. All of the processors inside each SMP are designed to perform the same computation, the same function, but are able to access different parts of memory. There's more to it than that. What does that really mean for us? Well, I haven't started to think about how I'm going to teach you multi-core computing on GPU. Yeah, that's quite a lie, actually. I've thought about it quite a lot. But I don't want you to worry about it too much, because today we're going to talk about memory allocation. Next week we'll talk about memory transfer and single core serial computation on a GPU device. The week after that we will start doing parallel computation on a GPU device. But there is something you need to think about in the next 2 weeks. The GPU is designed to use these thousands of processors to perform calculations on a single function. One function only. We can have multiple functions, but you cannot have these two different functions running at different times without creating some kind of problem. These are, of course, using different streams on the GPU, but we're going to talk about that later. These processors are grouped into groups, SMPs. The processors in each of these groups has access to some local memory and are able to see each other, but cannot see other streaming processors in other groups. They can't communicate with those at all. And in fact, the way the GPU schedules work to be performed across these SMPs, there's no way of knowing when or where any piece of work is going to be performed. So you can't rely upon communication between any SPs from different blocks to be safe. The only thing you can count on is that in any given time, any SPs contained within a single SMP will be working at the same time and will be able to see each other. But SPs contained in different SMPs will never be able to talk to each other, never be able to see each other, and will normally be scheduled to do different parts of the computation at different times. And we cannot control that. So it actually gets pretty tricky. So, it should be clear to you guys now, well, I hope, that any computations performed on the GPU will need to have been performed upon data that is held inside GPU memory. Those SPs can see other SPs and they can see memory on the GPU, but the SPs on your device cannot see memory on the host system. So we're going to need to find a way to allocate memory on the GPU device, copy memory into that memory from the host to the device, and then get our answers back. This computation will be performed by thousands of cores. How do we organize all of those thousands of cores to help share our work? This is not automatic. Give you an example. I have kids. They have one room. One kid to clean that one room takes about an hour. I tell two kids to clean that room. How long will that take? Yeah, thank you very much for that, Alex. It's not a linear relationship. You might think it goes twice as fast or twice as slow. It is very difficult to predict. If you have 1,200 kids cleaning that room, unless you have a very specific way of sharing that work, it is not going to work out for you. So you're going to have to be precise in explaining how you guys are going, how the kids, all of these thousands of kids are going to work together to solve this problem. Programming on the GPU is exactly the same as asking kids to clean a room. It is not automatic. You need to be very specific. And don't forget that computers are extremely stupid. So we have to be exact. There's another thing. The GPU is very different to the CPU. Your CPUs, your i7s, maybe your i9s might have up around 16 physical cores maximum. You guys at home will be using i5s, i7s that have 4 cores perhaps. This sucker, most GPUs have thousands of cores. It should be pretty clear straight away the memory is different. The controllers are different. The caching system is different. Your compilers, the ones that we've been using now, G++, GCC, are never ever going to be able to compile a GPU code to run on that architecture. It's impossible. So we're going to need a special compiler. And we do have a special compiler, and we're going to look at that today. So, today we're going to review, well basically my mission today is to teach you guys to compile GPU codes and allocate memory on the device, free memory on the device. But before I can do any of that, I need to show you the best way to allocate memory on the host. Because over the last couple of weeks, I've seen you guys write your C codes. That has been a very interesting experience for me. I know that many of you are using the worst possible way to allocate memory for arrays on the CPU itself. I'm going to educate you about the way you should be doing it. We're going to practice doing that. And then when you're ready, we're going to move on to allocating memory on the host, on the device, sorry. Let's do it. So, memory allocation, the way it should be done. So, up until now, there are a couple of things we need to note. I haven't asked you to create arrays in your codes yet. You've actually been able to avoid it. If you had attempted the two-dimensional advection diffusion problem that I provided as a practice problem last class, then you might have, well, you definitely would have needed to use an array then. But in most engineering problems, the ones that we're going to solve numerically, you must use arrays to solve. So, we definitely need arrays. So now's the right time to decide how to allocate memory. But before we get cracking, there's something I want to ask you guys. Memory inside the system that you're using, inside the CPU, inside the host. You might have, what, DDR3, DDR4 now. You've got DDR4. Have you guys actually ever seen how the addresses in memory are structured in your computer system? It is one-dimensional. It is basically like, nothing like Tainan or Kaohsiung. Instead, we have one road, and all the data that we store inside our memory is somewhere on that road. So, Zhonghua Lu, maybe we say this is Zhonghua Lu. And the memory that we want, the information that we want is stored on that street. It's not a grid. There are no streets coming off Zhonghua Lu. It is just one road, and all of our addresses are one-dimensional. So we store information in our computer systems in 1D. This is guaranteed. Some of you may be familiar with two-dimensional memory, two-dimensional arrays in C, C++. Two-dimensional array in C++ is basically starts with a one-dimensional array with each element of that array containing a different address. And that address goes to a different one-dimensional array. All of these arrays are not grouped together. They're placed at different points in your memory. And using two-dimensional data structures in C is a very inefficient way of storing information. And accessing any point of your two-dimensional data structure is twice as slow as actually accessing the same memory structured in a one-dimensional format. So what does that mean for us? It is true we live in a 3D world. So all of our calculations will be in 3D. Some of our calculations will be in 2D because sometimes 3D is too hard. That's fine. Never, ever will we use 2D or 3D data. We are going to solve 2D and 3D problems using one-dimensional memory allocations only. I never want to see you guys trying to use two-dimensional memory allocations. There are many reasons for this, but the most native and simple reason to understand is memory is stored in one dimension on your system. Same for the GPU. We're going to find a way to squeeze every bit of performance out of this as we can, and that basically means we're limiting ourselves to one-dimensional arrays. Let's get going. This is how some people might allocate an array on C, C++. This is the wrong way. This is the worst possible way. I don't ever want to see this kind of thing again. But when you guys do Introduction to Computers in your first year of undergrad, if you can remember back that far, no one can, but I remember teaching it. How could I forget? We have an array A. It has 10 elements. We allocate it like this. We can see here that we've got an array A that holds 10 elements. So we have a for loop that goes over those 10 elements. In C, C++, the first index of any array we look at is 0. In most other languages, like Fortran or Python, you can pick any number you like, even negative indices. But in C, it must start at 0, and you cannot have negative values. So we start at I equals 0 and go all the way up to 9. We have 10 elements here, but we cannot access A10 because that is the 11th element of our array, and we'll get a segfault for sure. So here we basically allocate A, we set its values to 2i, and we print its values. This is what we get when we run it. Very nice little system that we've got here. I have to ask you, where is that A stored in memory? Well, there's a reason that we don't do it this way. The variable A there is put on what we call the stack. Now the stack is a small piece of memory that the computer reserves for any thread, any process, any program that is running. And that amount is fixed and is constant and is created when we start our program. Now the problem being, sometimes when we create a program for scientific computing, we aren't sure how large our problem space will be. We aren't sure how many cells we need in our problem. We aren't sure how many elements we need in our array. But C doesn't care. The stack size is always constant at the beginning. So the only way to change the stack size is actually to go into the environment settings and change it through there, but it can't change dynamically. Therefore, what we see is sometimes 10 elements inside our array here are fine, but if you change that to 10 million, that's going to exceed the limit that is imposed on us by our stack. This program will run and crash, and it will not tell you why. It will run out of memory in the stack, but it won't tell you. There's no message saying I ran out of memory in the stack. It's not polite. It just stops working. So every year, students come to me and they allocate 100 million elements in this 1D array on the stack, and they ask me why it doesn't work. This is the reason. Stack is small, can't afford to have that much memory placed. So we need to use something called a heap. Heap is a part of memory which can grow and shrink as we require it to, and this is the place where we want to allocate our data. So what do we do? Well, on the stack, what we actually want to store is an address. Address for our memory that we're going to allocate on our heap. And then we're going to use a special function to allocate that memory. Oh, what function are we going to use? Here it is, malloc. There's a reason I'm explaining malloc to you, because the function for allocating memory on the GPU device is called CUDA malloc. It's basically almost identical to this. And so if you understand how malloc works, then you're going to have no drama whatsoever with CUDA malloc, more or less. So first we allocate float star A. This is an address which we store on the stack. So this star A is kept on the stack, but it points to an address in heap memory. Heap memory can grow and shrink as we need it to, and here is the function which allows us to allocate memory on that heap and returns to us the address in A. That's basically malloc. What do we have to do when we use malloc? Well, malloc returns a void or null pointer. So we need to convert its type. In this case, A holds floats and is type float star, so we need to say float star. We need to do a force type conversion there. And then malloc takes one argument. It can take more, but we use one. And this is basically the amount of memory that we need to allocate. In this case, we have 10 elements, and the amount of memory we're allocating is 10 times however big a float is. Size of is a very, very useful function in C, C++. So this is basically how we tell malloc how much space we need. You could work it out yourself and put the number there if you wanted to. But why would you do that? Just copy this. All right. The key functions are, well, there's one other function that you can see there that's different to the previous code, and that is down the bottom, free. Free A. Now, free is a wonderful function because it is what will save you from being killed by me. I need to explain this. When we use malloc, we reserve memory on the heap. It's a very powerful function which allows us to dictate how much space and how that space is reserved on the heap. However, with that power comes responsibility. Malloc reserves that memory, but if we do not tell the computer to clear it, it will remain reserved until the computer is reset. So we have 20 people in this classroom allocating memory using malloc. If you don't free that memory, it's going to stay reserved, and that means that every time some other application wants to allocate memory for whatever it's doing, that space of memory that was previously used will be inaccessible to that program, and inevitably my server is going to run out of RAM because you guys are going to keep allocating memory and not free it. But you guys aren't going to do that, are you? Because you're going to remember to free the memory. Every year there's always one student that forgets free and crashes my server. And I always know who it is, so I can't wait to meet that person. Free will save your life. This is what we call garbage collection. When a program is finished, there's often garbage left over that needs to be cleaned up. There are some packages or libraries which allow us automatic garbage collection, but this class is not about doing things automatically. It is about mastering the technology at the highest possible level. We're going to free it manually, aren't you guys? Yes, everyone here is going to free the memory they reserve on my GPU device. Obviously, this is for the CPU. The GPU equivalent of this function is called CUDA free. So changing this code to be a GPU code is a snap, and you will see very shortly. All right. Some of you will notice that this is a one-dimensional array, and that is all we're going to create in this class. I've already explained to you, we're never going to allocate more than one-dimensional arrays. We're going to solve 2D problems using one-dimensional data storage. That shouldn't be too much of a problem for anyone here. You might need to think a little bit about how we're going to do it. That's fine. I can actually give you an example. But before we do this, I want everyone to log into the server now. The port is 911. That's what number I will call if someone forgets to free their memory. It won't work in Taiwan. I know it's 119, but the port 119 is actually for something special, so I had to use 911. Log into the server. Write this code, please. Compile it and run it for me. Show me when you're done, and then we'll continue. All right, let's do it. Oh, that's loud. Sorry. Okay. So everyone now should have a working code which allocates a single one-dimensional array in malloc. If you haven't finished yet, that's okay. Download the PPT, the PDF, and continue. Now, what am I going to do for you? I'm going to do you guys a favor. In the back of your minds, I know that many of you are thinking very hard. How do we use one-dimensional memory allocation to solve a two-dimensional, three-dimensional physical problem? I'm going to save your lives now and show you exactly how we're going to do it. In the next 20 minutes, I'm going to be writing the code on the server, and I'm going to be using information on the whiteboard. You can choose to copy it down, or you can throw caution into the wind and not worry about it. This is a two-dimensional unsteady heat transfer problem. The problem I want to solve is this one here. We have a rectangular domain. I'm going to make the temperature here 1, and the temperature here 0, 0, 0. If you've taken courses in engineering mathematics or heat transfer before, you should know what the contours of the heat solution look like in the steady limit. The contours of constant temperature look more or less like this. Who remembers doing that in engineering mathematics? Everyone who took my course in engineering mathematics should be putting their hands up right about now, but I know they forgot a long, long time ago. Now, we have a two-dimensional problem. We're going to store this in one-dimensional arrays, or a single array on our machine. And what's more, we're going to use a single for loop to go over those values and compute the new temperatures as a function of time instead of using two for loops. So I promise you now we're going to be using one for loop for everything over one-dimensional array. First of all, our data structure. I'm going to create a grid. Now, of course, the grid I'll be creating is going to be much finer than this. In this case, in the x direction here, x and y, we have nx cells. How many cells do we actually have? 1, 2, 3, 4, 5. Can you guys see that from the back of the room? Okay. Here, we have n. I can afford a $100,000 GPU, but we don't have pens which work. Oh yeah, here we go. And there are 3 in this direction. How are we going to store this information in a one-dimensional array? It should be pretty straightforward. We're going to use a method which you guys will be very happy with. What is the index that we start with in C? 0. So let's start giving them names. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These are going to be stored in our one-dimensional array, just like that. All the way up. 0, 1, 2, 13, 14. And I tell you what, we'll even call it our array A. The challenge then is to understand which cells are to the north, south, east, and west of us. So let's have a look. Please let this red pen work better than that. Hang on. Let's see. I'll put that around the other side. All right. To go from cell I to its north neighbor, we can see its north neighbor, north from 7 is 2. So the way I've produced my grid here, we might say the north neighbor is 7, take away what gives us 2? 5. So there's I. This must be I minus nx using the indexing system I've created here. This one here is what? Yep. This one here, I plus 1, I minus 1. So it should be pretty straightforward. If our I is less than nx, we don't have a northern neighbor. It's our boundary, which will give us 1 in this case. If I is larger than nx times ny minus nx, then we're on the bottom neighbor, and we have no solvent cell. If we're here or here, or on the left and right again. And so we should be able to use these formulas to give us an idea of where our neighbors are in space. Now it's a bit of math time. Can I delete? Oh no, I need that. Oh dear. T nu, take away t divided by dt minus. Well, we're writing out the discrete form of the second order, or the heat transfer equations here. So that is going to be, let's see, in the x direction first, I'm going to write TL plus TR minus, I need that, 2T, divided by dx squared. This is times by some phi, minus possibly another phi, t up plus t down, take away 2t divided by dy squared. Equals 0. Our mission is to solve for the new t. That's our mission. So let's write the code. Oh, I love writing code in front of students. This is always fun. This is going to be quite a complex code, so bear with me. My advice to you is to try to keep up, or take photos, or just write down what I'm writing with your hand. You know, remember that thing you use sometimes? Let's get cracking. Okay. Since I probably want to be able to talk to you, I'll put the microphone back on my shirt. Come on, people. Where are we? Well, first, create a new directory for this. Now we start. Are you guys much happy with the new syntax highlighting and coloring scheme that I've got going on here? It took us freaking ages to get this working at the end of last class. Hopefully you can see what I'm typing pretty easily. When we write codes like this, remember the number one rule is to never try to write too much code before you compile and run what you've written, and then take minor steps to work towards the goal that you're solving. If I want to allocate memory, what do I need to do? I want to create an array. I'll call it A. It's a 2D problem, right? So I'll call this 50. I'll make that 50 as well. The length and width of our domain, I'm going to make it square because I'm what engineers like to call extremely lazy. We need to create variables for dx, dy. I'm pretty sure we're going to require them. But as a matter of fact, I'm suspecting that we don't need them. I'm going to come back to this because what's going to happen is when I calculate my new T, I'm going to make all of the thermal conductivities the same. dx and dy is the same. I need to multiply them by the same dt. So as it's going to turn out, I'm going to multiply each component by this maximum CFL number anyway. And we'll come back to that in a second. So first of all, we need to allocate memory. Well, I'll create a variable for this. Why not? Now, will this code run? Anyone see any mistakes so far? I'm going to make mistakes. I'm only human. I don't have a book here telling me what this code's going to look like. Sorry? Wait. Huh? Oh, I haven't finished yet. Calm down. Yeah, calm down. I've got to free it first. Calm down. All right. What is this all about? Why do I say if A free A? That's because if A is not a null pointer, it's pointing to somewhere in memory. So I'm just basically asking the computer to tell me, is this a valid pointer or not? If it is already pointing to null, then we don't need to free it because it's already not holding address to memory. So I'm just being careful here. All right, very good. I'll look at that. Does anyone see the mistake? Oh. Seg fault. Segmentation error. There's an error in here. Can anyone see it? I did include that bottom bracket. No seg fault. Looks like it worked. Looks like, but I haven't got any memories, any information in there. Okay, let's do it. We need to set an initial condition for this. You'll note that I'm declaring I up here. I'm going to say the initial temperature in my block is 0. Do I have to write this? Yes is the short answer to your question. If you don't say that A is 0 for every element of A, there's a chance that there might be some garbage or rubbish in the memory that is located in the heap, and that your calculation might be screwed as a result. All right. How many time steps? Tell you what, I'll just write that in. 4, K, and I need K. We'll run 10 time steps to start with. So this is our transient loop. Now, we have to think a little bit about what we're doing here. We're going to go over all of our cells, cells 0 to 14. That's all 15 cells in this case, but we have more cells really. And we're going to, for each cell, compute the new temperature. So we're going to start in cell 0, and we're going to say, oh, his new temperature is his old temperature. Take away some of this, which is like 1, and to his bottom, and to his right, and to his left, blah, blah, blah. We're going to get a new temperature. But then if we save that new temperature here, we're going to have a new temperature in this cell. Then we're going to start computing the temperature in this cell. But on the right-hand side of this cell is the old temperature, but on the left-hand side is the new temperature. So we've just shot ourselves in the foot. Actually, this is a mathematical technique that we're using here. I'm not going to tell you what it is yet, but what should be clear to you is we need to find a way to compute and store the new temperature in a different array to the original one. We have A, which is going to hold our T, but we're going to compute the new T, but we can't store the new temperature in the array that we've created that holds our old temperature. Otherwise, as we're computing cell I minus 1, cell I minus 2, they're all the new temperatures, but cell I plus 1, I plus 2 are the old temperatures. So we need to be consistent in time. If we're solving for the steady limit of that computation, and it doesn't matter so much. But for unsteady calculations, we need to store both solutions, the old one and a new one. So we're going to need another array, a new. Can you see that? Yep. And if I want to survive, I'm going to need to free that too. Okay, very good. It's compiling. All right, and I may as well, do I need to set what my A new is here? Not particularly, because in the first time step, I'm going to compute the new temperatures based on the old ones anyway. So I only really need to initialize the old temperatures. Let's do it. Now inside here, inside our for loop, every time we want to compute the new temperature, we need to compute the new temperature across all of our cells. So we're going to need another for loop. To iterate across all of our cells in space. So this here is the spatial loop. That's a mistake. Sorry, this keyboard is funky. So this loop is in time, this loop is in space. You might be thinking, why do I have to bother showing you all of this? It's because when it comes time to start doing parallel computing, in parallel computing we have a concept called loop sharing. Some loops can be shared in parallel processing to make it faster, but some loops cannot. We cannot parallelize time. We can parallelize space. And this is why I'm making this extremely clear. If you try to parallelize that outer loop K, bad things are going to happen. Very bad things. All right, now we want to compute A new. If we want to compute A new, the best thing is to compute what is up, down, left, and right. So let's create some array variables that help us know what that is. Float, left, right, up, and down. I tell you what, we may as well compute our indexes too. IX, IY, which will tell us I'll just use X and Y index. So let's see. If I want to go off the system that I've used there, if I want to be able to use this to compute my current index, so let's say this is ij. If this is I and this is j, well, j is going down, I is going across. This one here is going to be 0, 1, 2, 0, 1. How do we get that information from our list? Anyone have any ideas on how we can do this? Any ideas? Any takers? No? Let's have a look at that. What is 7 divided by 5? 1 point something, and we round this down to an integer, we get 1. What is 12 divided by 5? 2 point something, divide that, round that down to an integer, we get 2. So we know we can compute the j index quickly by rounding down. So that's what I've done here. I've taken I divided by nx and forced it to be an integer. Then how do I calculate the rest? That'll do, won't it? Does that seem to make sense? That's 1, that's our J index. 2 here is 7, take away 1 times 5. So that's how we're able to do it. Of course, you guys can use any method you like for mapping your two-dimensional space into one-dimensional space and vice versa. But this will work. Now, let's have a look. If IY is larger than 0, that means using the data that we've stored here, we can look to the north, right? According to the way I've structured this on the board. So that means the variable that we've got for north is up. Up equals A daughter. I minus. Help me out, people. NX. Is that right? We just talked about that, didn't we? If this index here is larger than 1, then we have J minus, I minus NX. Gives us the temperature to the north. That's the index to the north. What happens if it's not? Up equals 1, when? South. If IY is smaller than what? Is that right? You can see how you're going to get burned here if you don't forget that, if you forget that 0. Oh, 0. Make sense? IX will tell us where we are in that respect. This is the X direction now. If IX is larger than 0, that means the left is I minus 0, I minus 1, is that correct? Otherwise we're on that bound. And the right temp that's awesome. And the new temperature, which is A new, is equal to the old one. How do we get it? We move all of this junk to the right-hand side. I'm incredibly lazy. You may have noticed my nx equals ny and my L equals h. So dx equals dy. So all of this can be factorized. I'm just going to have some constant, which is going to be my CFL number, the FTCS scheme, times by this plus this plus this plus this minus 4 t's. I'm going to be pushing my luck with stability. My CFL will be 0.45. And we have left plus right plus up plus down, take away 4 times AI. There we are. Does that make sense? Have I made a mistake yet? Yeah? Oh, CFL. So let me clarify just a little bit. All right. Someone just asked about the CFL. Yeah. Back in the old days, we used to have to lift these with our hands, which was actually faster. I wonder how many people have drawn on this. So, I'm going to multiply all of this by dt, and then move it over the other side, and then plus that t over there. So we're going to have plus dt phi divided by dx squared. Now if dx and dy are equal, and I'm going to pretend they are, then we're going to have TL plus TR plus T up plus T down, take away 4T. Yep. Now, this guy here, there are rules about this guy. We can't just have it being any value we like. If you perform a stability analysis on this finite difference scheme, we can tell you that this value must be less than or equal to 0.5. This is a stability criteria. And this is called the CFL number for this scheme. So we want this to converge to steady as quickly as we can. I want the largest safe dt that I can get away with. The largest possible value of dt will give me the largest possible value of CFL. If I'm pushing my luck honestly and truly, I would make this 0.5. I'm going to be a little bit more cautious and make it 0.45. Now, some of you are probably wondering, how are we going to make sure that this code is doing what I want it to do? Quite simply, if I really was keen, I can set nx equal to 5, ny equal to 3, and then manually check to see if my indices are going to give me the correct value. Do you want to do that? May as well, yeah. Oh, we're here. We're not going anywhere. nx equals 5 and then y equals 3. Of course, now all of our dx and dy's are different. I give 0 cares. We're just checking to make sure everything is correct. So I'm going to create a special section for debugging. Print of cell equals, so D, that's I. We want to print IY and IJ, or IX and IY, sorry. And I'll put a pause in so that we can see each one. And I'll separate them. All right, it's cooking with gas. And I'll tell you what, I'll disable this for now because we're debugging. All right, very good. Oh, my bad. I'm such a slacker. Did anyone see what I did wrong? My goodness gracious me, what a rookie mistake. Hang on. Okay. Cell 0. Well, let's write these on, shall we? This is 0, 0. And what's this one? 1, 0, 2, 0, 3, 0, 4, 0. This one here is 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, etc. Let's check. So far, so good? So far, so good. Now, unfortunately, we've got that time loop I need to negate around. If I press Control C, my program will finish, but then what will I not do? Free the memory. And then I would force myself to punish myself for not freeing that memory. So I've just had to step through here. So we can see that our code seems to be producing the right index. What else can we see? No segmentation faults. So when I set the values of temperature to the left, right, up, and down, I accessed A. Let's have a look at those. Hang on, let me clear this. Clear, come on people, there we are. Oh, whoops, nano. So you can see I do set the values of up, down, left, and right. If I made a mistake with how I computed the indexes, then I would have had a seg fault when I accessed the wrong section of A. And I didn't. So I would say that I'm okay. 50 and 50. 10 and 10. Keep it real. Now I've got this value of A new. After I've got that value of A new, what do I need to do? I need to copy it across every value of I. So I need another loop now. Yeah? Update the new value. Update my array to hold the new temperature instead of the old one. Okay, I think I'm cooking with gas. There's one other minor detail I need to do first. Before I leave here, I may as well take care of this. I need to save my data somewhere, don't I? So I need to create a file. Do I really need to? Yeah, I guess I do. How are we going to show the data? Oh boy, this is the sucky part, but I may as well do it properly. We need to go over and save every element in this, but we want to pack this data into a rectangle so that we can look at this result conveniently instead of just printing a long one-dimensional result, because that sucks. So I want to basically start printing this to a file and only insert a new line when I get there, when I get to the end of this line. Yeah, all right. Yay. Luckily, I have a mechanism for this. We already have a way of computing this. I'm lazy. That was it, wasn't it? and we're cooking with gas. Let's run 100 times. Oh, crap. Everyone shut their eyes for 2 seconds. Go. You can see I've controlled C out of this, which means that in my server now, I've allocated 50 times 50 times size of float in memory, which will not be freed until I reset my server. Luckily, that machine has like 200 and something gig of RAM. I think I'll survive for a little bit. Oh dear. All because I debugged for you guys. It's my fault. I don't feel like waiting. Done? There's our data. Did it work? Look at those numbers, man. No way. Oh, I love debugging. Let's have a look after one step. Was that rubbish? No, that was the correct thing. All right, that seems sensible. Is that correct though? Well, first of all, hang on. This was 10 by 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just making sure I've got the dimensions all nice and neat. So if we have initially 0, 0, 0, 0, and 1 on the northbound boundary, and we have this formula, and we're using 0.25 there. Does that result make sense? Seems reasonable to me. What will the next one be? Well, let's find out. Two. Yeah? Sorry? Keep going. Maybe 0.45 was just too ambitious. Let's try 20. What are we looking for here? I can tell you what we're looking for. Well, yes, we're looking for that. If your temperature is greater than 1 or less than 0, you're screwed. The hottest temperature in this 2D problem is 1 on the north boundary and 0 around the others. If you see negative temperatures in physics is a very bad thing. And if we have temperatures higher than our hottest temperature in our thing, we also know that we're in a bit of trouble. Let's run it for a little bit longer. It, 40 time steps, that's right. Looks okay. So let's copy it across and use MATLAB to contour that. It can't fit on properly, so it's squishing around. The IP is not changing. The port changes. Yeah, every week. How long will it stay open until the end of the semester? Hang on, I can't download. Can I download to? I can download to downloads. That's right. Thank you, Chen Gongler. Now I'm going to open MATLAB and we're going to wait half an hour for that to load up. So, how was your weekend? What did you guys do for your holidays? I went camping. It was like a typhoon. It was in the south. I went to Shuhai, a place on the east coast of Taiwan, and the winds were 60 kilometers an hour all the time, and my tent blew down. And some other, and Kurlian Xiaojie, she was in her own tent, and she actually got blown away. And she's stuck in the tent, and the wind is rolling the tent around, and she's rolling around inside until it hits a car, and then she crawls out. And she's not injured, but her hair is everywhere. Oh, so that was my weekend. My whole body is aching. Come on. Yeah, all right. There's our data. A is a 10 by 10. Yay, thank you, I passed. I'm now qualified to teach thermodynamics, heat transfer, and computing. So, we know our code works. It's symmetrical, and it looks more or less what we're here. We're not steady yet. This is not the steady result. 40 time steps for this domain was not enough to read steady. But you guys can muck around with that on your own time if you guys want to see how it worked. So, the temperature in a grid. Yeah. Sorry, so when I used FileZilla, I copied the test.dat back to this machine and then used MATLAB to contour it. There's a very good reason for me going through all of that business. Two reasons. One, for you to see what I had to do to perform a two-dimensional computation using one-dimensional data. Because you're going to be writing codes on the GPU, and you are under no circumstances whatsoever to be allocating two-dimensional arrays on my GPUs. Because if you think about how you allocate it. If you're going to use malloc to allocate two-dimensional arrays, first use malloc to create an array of addresses, and then use malloc n times for each address that you're allocating. If you delete the array of addresses before you delete the arrays of information, that means that you've got n, all your data is still inside memory, but you've lost the keys to access that data and you can't free it. It is a very dangerous thing, but mostly to do with performance. All the information is held in memory in 1D. If you want to squeeze every bit of performance out of your machine, you're going to be using one-dimensional arrays anyway. Fun stuff. Now there's the part where people pull their hair out. You can see I don't have a lot of hair left. When I first started using GPU computing, there was no internet for this stuff. There were no books. There was no online reference. And there was exactly one person in NVIDIA who knew how to do this stuff. His name was Nathan. He's a good mate of mine. He's actually quite famous now, Nathan Bell. You can Google him. Anyway, let's do it. So, we are not going to be using GCC or G++ to build these applications. When we write stuff on GPU, we're not going to be able to use those compilers. We're going to have to use NVCC. NVCC is the name of the program which compiles our CUDA applications. It is the name of the compiler. And the language that we're using is called CUDA, but it is basically C. It's not C++, it's C. So, the very first thing that you guys should be trying right now is at your login on the server, you should be typing NVCC and pressing enter. If you type NVCC and press enter, and it says, I don't know what the hell you're talking about, that means that the administration has not yet set up the correct directories in your environment for you to know where that executable is. So my advice to you is do that now. See if you can find NVCC. If you do not have access to NVCC through your current login, don't panic too much. I'll come to you and fix up your bash script very shortly. If you do have it, it's going to be basically asking you to provide some input files. Shout it. Little NVCC. Just type it in. The computer won't blow up. Yeah, it worked. See? No input files. Yeah, like, watch this. NVDD. What the hell is that? Yeah, that's what you'll get if it didn't work. NVCC, it works if it provides you some sensible feedback. Now, just like G++ and GCC, NVCC is a compiler and a linker. We are able to compile codes and we're also able to build executables. CUDA is very good at building, CUDA is very good, or NVCC is very good at compiling GPU codes. NVCC is not good at building executables. It can do it, but I would not advise it. So here we've got two commands here. NVCC file name -o test.run. This will compile and build your executable. So we're taking two steps. We're compiling and linking, and we're able to make a run file using NVCC. Here, we're just compiling. Which one do you think I'm going to ask you to do? Today, I'll give you a one-time special. I'll let you get away with doing this at the beginning. But, like I said, NVCC is a program for compiling GPU applications. It is not a compiler for building CPU applications. The ICC compiler, the PGI compiler, GCC, G++, these are all stronger, older compilers for building CPU applications. NVCC is a compiler for GPU. So, you can compile and you can build and link with NVCC. I'm going to talk to you now about how we can work our way through and compile using NVCC, but use G++ to create our application. So, I'm not going to do this, but you guys can muck around with this if you like. NVCC can compile this code. Now, the code that you see here on the right-hand side, is that C or CUDA? Yes, is the answer to that question. It is C and it is CUDA. It looks a lot like CUDA to me, and is basically something which your NVCC compiler will be able to understand. So this is a very simple C code. If you use NVCC to compile and build it, it will work. In fact, any example today that I've used, NVCC will be able to compile and create an executable for, including the heat transfer code that I just created just now. NVCC will have no trouble. Is this the best way to do this? Definitely not. Most simple engineering codes written in C will be able to be compiled and built into executables using NVCC. It is a bad idea. It is like, you know, a race car is an excellent car for driving on a racing track. But it is not an excellent car to drive to Taidong on the 1010 weekend holiday. Because the number 9 freeway is always chockers, and there's a traffic jam, and the maximum speed you'll be driving is 5 kilometers an hour on the number 9 freeway. So there's no point in having a racing car. NVCC is for compiling GPU applications, not for building executables. There are some differences between CUDA C and C. In CUDA C, we cannot have recursion. If your algorithm uses recursion and you want to make this run faster on GPU, I've got some bad news for you. It's not going to work. That's my bad news. End of public service statement. There's also no function pointers, but seeing as you have mostly probably never learned what a function pointer is, I don't think that matters much. If you're familiar with what a function pointer is, maybe you took Professor Feng's class and she taught you what a function pointer was, and you still remember, then maybe you will know, but we're not using function pointers in this course anyway. Otherwise, you should be able to compile. But we don't want to do that. So what I just showed you before, using NVCC to compile, build, and link your application, or link and build, is basically this step here. We don't want to do that. We don't want this. We want to use NVCC to take our source code and create a machine object, an O file. Then we want to use a more powerful compiler to take that object and then create our executable code. So this is two distinct steps. There's a reason I taught you these steps, because we're going to use NVCC to take our source code and create an object. Then we're going to use G++ to take our object and create an executable. Two unique steps. Never ever do the same step using a single compiler. We're going to presume that G++ is a stronger compiler than NVCC, and most of the time it will be. So our steps can be broken down into two parts. Use NVCC with -c first to create an object. That will give us, if in this case we've got NVCC space test.c.c, -c, sorry, that will create test.o. Then we take test.o and we use G++ to create our executable from that. So G++ test.o -o test.run. That will take our object file, link it, and create our executable file. Then we can run it. Piece of cake. In this case, this will work. There are only a couple of problems. One being, when we use G++ there to take our GPU object, that is an NVCC object, we're linking and we're going to create an executable that is potentially capable of performing GPU computations. Now, G++ is used to creating applications for the CPU, the host. There are some libraries that it needs access to in order to create an executable which will be able to use the GPU. We're going to talk about that very soon. But first, why do we do this? Performance and reliability. I think I made it clear to you. We should use the strongest possible compiler to take our objects and create an executable code. We use NVCC to compile our GPU code because NVCC is designed to be a strong compiler for GPU codes, not for CPU codes. That's what it's designed to do. Oh yeah, anyway. Oh, now of course we can't use G++ to compile everything. G++ doesn't know anything about GPU, so we can't use G++ or GCC to compile our CUDA codes because that poor little compiler has no clue whatsoever about the hardware on the GPU device. So, today's class, we're going to create a single executable. That executable is going to be comprised of 3 files. One header file, one CUDA file, and one CPU file. So that CPU file will be called main.c. Our GPU code today, will be GPU main.cu. CU for CUDA. Before you ask, yes, every CUDA code must end in .cu. If it does not, NVCC gets very upset. So we have 3 files, and that GPU main.h is just a header file. So it's not really a code, it's just a header file which we're going to place in both of those codes. What are those codes? Come on, there it is. We've got main.c on the left. Main.c on the left is just our GPU main.h. You can see we use commas here. We do not use those larger than and smaller than brackets. The reason is because when we use those larger than, smaller than brackets, we're referring to the standard library of header files. C knows where they are, G++, GCC knows where those are. In this case, we're using a header file that we ourselves created, and so we have to specify its name. Then you can see we've got int main. Int main is something which executes on the host always. So int main must be placed in the CPU file, the host file. So you can see here, if you have a look at this code, all we're going to do today is allocate memory, free memory, and basically return. There's nothing magical here. All the magic happens inside these functions. So from the perspective of the computer when it compiles this is saying, oh, there's an allocate memory function, a free memory function. They're declared here and they're defined in another object which we link together with this when we perform our build. Here's our header file. So our header files just contain our standard stdio.h and standard libraries. We define n here so that, well, basically if you're going to have arrays, you can use integers to hold the array sizes, but if they're not going to change during your computation, you may as well replace them with what we call symbols. N is a symbol here. So by defining n equals 100, the compiler will then go through your code, find wherever n appears and replace it with the number 100 when it compiles. And then the purpose of a header file is for us to declare the functions we are using. And that's all we do here. We declare our allocate memory and free memory functions. So we can see we can use this header file on both our main and our GPU main file on the left and right hand side. On the right hand side is our magic. That is our CUDA code. Now let's have a good, nice long look at that code. At the top we've got GPU main.h, that's fine, we're just wanting to include this stuff. You can see there's no CUDA.h up here. I haven't included CUDA.h, that we don't need to because we're going to use NVCC to compile this. If we use NVCC to compile this, the compiler knows what's going on. It is a CUDA compiler. We don't need to worry about including that stuff. So, HADA. We're going to store an array. I'm going to call it A. What does D and H mean? Yes, that's exactly right, host and device. So I deliberately call my variables different names so that when I look at the names, I know where those variables are. Because if I have variable A and B, and I just say float star A, float star B, by looking at the name alone, I can't tell where that variable is. If I try to type printf AI, well, it will work here if I printf HA, but if I try to printf DA, DA is on the GPU. Printf is a CPU function. It can't see what's happening on the GPU. So there's no way we can use printf to print a GPU device variable, which presents a problem for us. If we have data held on the GPU, how do we know what's inside it? You have to move it. So we're going to get to that soon, but not today, because today we're just going to look at allocation. So we've got A, or for the host, D for the device. Of course, because I'm a master code writer, I've got comments here which tells you exactly why and what they are. Then we go through. I use a size type, size underscore T, size type variable size, to hold the number of bytes that my variables require. In this case, n times size of float. You might remember last time I just used malloc and I put that variable in there directly, n times size of float. You can see here when I use malloc now, I just put that size type variable in. That's pretty handy. So that doesn't take the number of bytes, it can, but in actuality it takes the size type. So it's actually a very neat, possibly overloaded function. So here we allocate our host memory. Forced type conversion to float star, HA is a float star, malloc, our size. Then underneath we've got CUDA malloc, here we are, your first GPU function. This is a special function which allows us to allocate memory on the GPU device itself. Error equals CUDA malloc void star star and DA. Many of you who took my computing course in the first year will have very fond memories of arrays and addresses and indexes and references and all of this stuff. You don't have to fret too much about this because, one, we're going to allocate all of our memory for these functions inside our codes and not in other functions. And so you don't need to worry about passing references to references or pointers to pointers or references to pointers. Just copy my code. That's your mission today. Copy my code and not break my computer. So we're going to take it nice and slow, and you'll have a chance to break my computer next week. We have a chance today. So let's have a good look at this. We've got CUDA malloc for allocating a memory. It doesn't return the address. It doesn't return the address because this is a CPU code. It is performing work on the GPU, but at the end of the day, this is being executed by the CPU. CPU doesn't have the right to know what the address is for this stuff. That's not for you to know, because that's memory for the GPU device. What it actually returns is an error type, which is the only way at the moment for you to know whether or not this operation succeeded. So in C and C++, every function returns a type, every single one. malloc returns a pointer to a type. Size of returns something. Even printf returns something. Printf returns the number of characters in the sentence that you're printing out. So every function that you use in C, C++ returns something. This CUDA malloc returns a CUDA error type. Then we can use printf, and then another function, CUDA get error string, and then we use this error type as an input to this to ask the GPU, hey GPU, I just asked you to do something. What do you think? What happened? Did anything happen? Now, I would say you've got at least a 50% chance then of the GPU being honest and telling you what happened. Only a 50% chance. There is a 50% chance that something went wrong and the GPU won't tell you. It's like when you ask your wife, are you okay? And she says, I'm fine. It doesn't mean she's fine. You could be in big trouble. But it's a step, a first step towards making that progress. So, what else do you need to know? Oh, we've got a free memory function. If HA, free HA, you don't need to put that if HA in there. You can just type free HA. CUDA free. CUDA free to free our GPU memory. Please try to remember to free my GPU memory. You guys will be using a C2075 GPU today. It has 6 gig of RAM, only 6. My server has 200 something gig of RAM. If you forget to free, I'm sure it will be fine. Use up all my memory on my GPU. It's only 6 gig. I will need to reset it. Good news is, I can reset the memory on my GPU with a single command from the terminal. I don't need to restart my whole machine. But it really comes down to how lazy I am, because all I need to do is walk up to the back of my machine and pull the power out, and I've just reset all my memory for my CPU and the GPU device, and shut my machine down in a very unsafe fashion. But it's Linux, it will survive. To start, what do we do? Let's see. We've got 2 codes here. We've got a main.c and a GPU main.cu. We need 2 compilers to do this. G++ to take our C. I know I'm using G++ to compile a C code here. Don't think too hard on this. Otherwise your heads will explode. This will create an object main.o. Then we've got nvcc GPU main.cu -c, sorry. That will give us GPU main.o. So now we have 2 objects we want to compile together to create a single executable, just like this. Now, the real challenge is we're going to use G++ to link these. Inside our GPU main.o, there are important functions that are for the GPU. We've got CUDA malloc and CUDA free, and we've got the CUDA get error string. Those 3 functions. Now, inside NVCC, we have automatic access to the header file, CUDA.h, but we don't have the precompiled libraries containing those functions. We need to add them. The precompiled libraries are L CUDA and L CUDA RT, runtime and CUDA. So when we use G++ to compile these objects, we need to tell the compiler, hey, this object here has some CUDA stuff, and we need to link those libraries to our executable. So we have to do 2 things. 1, we need to tell the compiler where those libraries are. So G++ main.o, GPU main.o, these are our 2 precompiled objects. -L says, hey, Mr. Compiler, I've got another directory that holds another set of precompiled libraries you need to look at, and has the directory. This is a special active link directory on my Linux system. You guys are going to cut and paste this because it is going to be the same as what you have access to on your servers, on my server. Then which libraries we're linking, and then -o test.run. That will do it. That is how we compile our thing. If you wanted to cheat, and then you wanted to say, screw it, I'll just use NVCC to build my application, that's fine and dandy. For the final step, instead of doing this, you can do nvcc main.o, GPU main.o, -o test.run. You don't need to include these libraries because NVCC, being smart, will know you're probably using NVCC because we're doing CUDA work and we'll probably automatically connect those libraries to your linking anyway. I want you to do this. I don't want you to do the bottom one. I want everyone here to use this method to create their executable. Now, some of you guys are very fast typers. Some of you are not. I've been watching. Every time you want to compile your code, if you have to type in this long line, that's a bit of work. Your fingers are going to get very fast very quickly. If you want to become a very fast coder, a very fast typer, by all means. Every time you recompile your codes, please use this method. Just type in that entire line. But there is another way. Make a makefile. So now it starts. A makefile is a script which allows us to automatically, or well, that's the correct word, automatically take our codes, build them, compile them, link them in a way which is satisfactory for us. So let's have a look at this makefile. This is a makefile like I discussed in the first week. I didn't make you use a makefile, but I would recommend using a makefile now because now's about the time that we start programming GPU applications and we're going to be doing a lot of compiling. No one's code ever works the first time. Everyone has to compile at least 5 times before we're done. Using a makefile, we're able to compile those really quickly. First things first, we introduce a variable called CUDA_lib, which tells us the location of our directories and adds on, while we're here, those libraries CUDA and CUDA_RT. That's not the magic. That's just a variable declaration. So we can create variables and scripts by using ... equals 2. Now, what is really interesting is what happens when we run this. When we type make after we've created this makefile, the first thing it will do is go to all. And it will see these labels here, CPU and GPU. If it sees a label here, CPU, it's going to search the rest of the script and see if there are any declarations of labels or definitions of labels underneath. So it's going to search for CPU, and underneath here we've got CPU ... That's a label. And it's going to say, okay, here I'm going to do this computation first. I'm going to follow this instruction first. So when I type make, it's going to go to this, it's going to hit CPU, and it's going to come down here. It's going to type g++ main.c-c. It's going to perform that computation automatically. Then when it's finished, controller's going to return up here and it's going to say, oh, GPU. Then it's going to run down here and do this, nvcc gpu main.cu-c. That's going to create gpu main.o. Then it's going to jump back up here and say, okay, I've done everything that was asked of me here. Now I can perform this instruction here. g++ main.o, gpu main.o, all the rest. And this is how we access the value of that variable using the $ sign that's in brackets. So by typing make and then pressing enter, we can compile using NVCC, compile our CPU code using G++, and then build our application using G++. So all of those 3 steps are performed by typing make once. It's a very powerful tool for automating or increasing the speed at which you perform the work. So how you want to do this today is up to you, but I highly recommend creating a makefile. If you go onto the notes for this subject on my website, not the slides, these are the slides, but there is actually another PDF for notes. In my notes, there's actually a whole section which describes to you how to create that makefile. And I believe I've provided details in there on how to do this exactly. But here is the makefile that you can use today. So today, this is what I want you to do. Well, right now, this is what I want you to do, and we've got more work after this. I want you to write these codes. Write these codes, create your makefile, and make and run it. If it runs perfectly, your CUDA code will say that everything ran smoothly, and it's going to say CUDA error malloc DA, no error. If it gives you some other error, that means actually there are a number of errors that could go wrong, but I'm pretty sure that everything's going to be fine. Go for it. Go ahead, copy those codes, create your makefile, and show me when you're done. All right, before I let you guys get away with yourselves, this is not the final activity of the day, and this is not the end of the lecture. There's actually something I want to show you before we get too far. I want to talk to you a little bit about error reporting. So if your code doesn't work yet, that's okay, you guys can keep working on it. But error reporting in CUDA, you guys have had a glimpse at already. We use the CUDA error type to report errors back to us. In the code that you just ran, this is the one. This is the code that we looked at. We use error equals CUDA malloc. The error variable contains information regarding our error. 如果你没有很清楚那个 error type 是什么用的呢，最好听一下。Because I'm not going to repeat myself after this. That error variable there is a CUDA type which contains information about any errors which a GPU might have. 那个 GPU 没办法跟你说我没有成功啊，你用 CUDA malloc 的时候，它没办法跟你说我有成功还是没有成功。Only through that error type will you know if you succeeded or not. Because if you, at the moment, this code that you've written, we don't do any calculations, we don't copy data to the device, we don't copy data back. There's no way for us to know if you've actually succeeded or not until you do this kind of work. So 现在你只有一个方式, you only have one way of doing this now, that is through examination of this CUDA error type. 如果你真的完全没兴趣那个 error, then you can leave this error type off. You can ignore that if you don't have any interest in looking at what that error is. Just like printf returns a number of characters in your sentence, in the string that you type, every function returns a type, and you can ignore it if you want to. Do not ignore them. So in the code I gave you, there is a CUDA-free function. CUDA-free also returns a CUDA error type. I did not check what that error is. I would advise you carefully. You should probably modify your codes to say error equals CUDA-free, to have a look to see what errors could be resulting when you attempt to free that memory. Error is a special data type. It's CUDA error type, which is this type down here. It contains a lot of information. It is not a string. It is not a character. It is not an integer. It is an object which holds a lot of valuable information. To extract information from that, we need to get the CUDA get error string, which is that function there. So CUDA get error string basically returns the error in string form and allows us to print its value. Why do we do this? When we perform operations on CUDA, we cannot use printf or cout in our GPU codes. 我是希望你们有准备好这个问题. In a normal code, we can use printf to return our errors. In GPU, we cannot use printf or cout to return errors. We must use more advanced techniques, and the CUDA error type is one of them. What error types are there? Oh, I love these pages. So every year, with every different version of CUDA, this list grows. No errors is the one you've already seen. It is also the one that you hope to see, and you do not want to see anything else. But there are a lot of errors. You can have a look at them. My favorite two errors are the unknown error condition, where the GPU does not know what went wrong, and the not ready error, where the GPU is not ready. What do you have to do? You have to whisper to the GPU, are you ready yet, before you start? When we perform our calculations, I promise you, there will be at least one person here who sees the unknown error. And what is the next one? Initialization error. There will be someone in this class who triggers an initialization error. Reading these errors is critical to understanding what went wrong in your code. Do you see a segmentation fault error somewhere in this list? I can tell you there is not. When you get a seg fault on the GPU device, it will not tell you that you got a seg fault on the GPU device. But what will happen is that there will be a launch failure or an initialization error when you use the next GPU function. So don't fret too much. Have a look at these. Not ready error, that's a great one. Today's exercise. So the thing I was just asking you to do is basically just a warm-up instruction, but I'm giving you a freebie because today's class, I've just asked you to allocate memory on the GPU, but I haven't told you how to copy data or how to start launching computations on the GPU device yet. So because that information is pretty hardcore, we're going to leave that to next week. Today, I want you to work on your minor assignment. What the hell is a minor assignment? Minor assignment was the assessment item I gave out on the first day of class. It is on the website. If you scroll down a little bit, the PDF is there. This year's minor assignment is basically group work. You have to complete this assignment in pairs, not by yourself and not with 3 people, 2 people. If you are by yourself, then I'll allow you to join a group of 2. But you have to talk to me first. I want you to write a parallel program which allows you to compute the flow of water through a pipe network. I've been really nice. In the PDF, I've actually given you 2 codes for this pipe network. We have a volumetric flow rate of 10 cubic meters per second coming into node 1. This node here is just a junction where pipes join together. So we have a T-junction here. Water is flowing in here. Some water will go down here, some water will go down here. R is a restriction factor. It's related to the pipe diameter, its friction factor, its length. It's actually from fluid mechanics. If you remember your fluid mechanics and you remember how to compute head loss, that R is from there. I've given you some information in the PDF that is given out with this minor assignment. It doesn't matter what it is. A larger value of R basically means it is harder to flow through. That's basically what it means. So when the water gets to 1 and has a choice between going down 1 and 5, it probably will want to go down 1 more. But how much will go down 1 and how much will go down 5? And when it gets here, it sees an option between going 1 or 5. It will probably go up this way. And it can't go back up that way. It will probably go this way to the exit. Compute. Oh no! So 1 can be negative, that's right. Yeah. So you can have an assumption and then be wrong about that. So how do we compute the flow through this pipe network? I've presented you 2 methods. One is the Hardy-Cross method, developed by a very, very smart man. Another method is the Newton-Raphson technique. Newton-Raphson is a root-finding method for basic nonlinear equations. The governing equations for this system are nonlinear, and we have a system of them. Inside the PPT PDF file, inside the PDF for this minor assignment, I've shown you how to compute the governing equations. We have a collection of nonlinear governing equations. In this case, we have 5. We need 5. We've got 5 unknowns, the flow rates through each of these pipes. So we need 5 equations to solve for these 5 unknowns. 3 of them are linear, but at least 2 of those equations are nonlinear, which means we can't use substitution directly to solve. So we need to use an iterative technique to solve. Newton-Raphson is a method for solving systems of nonlinear equations. That's quite complex. Mathematicians in this room might be very interested in using this approach. Engineers, on the other hand, will normally go Hardy-Cross, depending on your preference. A long time ago, the whole world used Hardy-Cross for these pipe flow computations. In recent years, we've switched over to Newton-Raphson because Newton-Raphson will converge on the solution in 2 or 3 iterations. Newton-Raphson is very fast for this. Hardy-Cross is a bit slower, but there are strengths and weaknesses for each approach. One of them is going to be very easy to parallelize. The other one is not. And the parallelization methods for both will differ. I can tell you right now the Hardy-Cross method has a higher parallelization factor than the Newton-Raphson scheme. On the GPU, Hardy-Cross is going to go faster, I promise you this. But Newton-Raphson converges faster. So you have a devil's choice. You have to decide which one of these methods you're going to use. I already can tell you most of you are going to go Hardy-Cross. I would advise it. But I've given you the MATLAB codes for both. So I want you guys to use today's session to, 1, make sure you finalize who your partner is for this work. Pick a friend, probably someone who's smart. Work with that person today. I want you to try to finish part 1. There are 2 deadlines for this. The final deadline is the 13th of December. But you have a progress report to submit to me by the 22nd of November. If you have a look at your PDF for this minor assignment, I've given you the code and the instructions for solving one small network. Let's have a look at and I've also given you a bigger network to see if you know what you're talking about. Let's have a look at that one. hang on a second. All right, here we are. Teaching. See, I've got the graphics now. That's nice. GPU, assignment. There is our small network of 5 pipes and the equations. N here is most of the time equal to 2 or 1.85. It's a constant. Here's our Hardy cross code, Newton-Raphson code. This Newton-Raphson code is we require to find the inverse of a 5 by 5. We have 5 pipes with 5 unknowns. We have an inverse of a 5 by 5. If you have 20 pipes, it's the inverse of a 20 by 20. If you have a million pipes, it's the inverse of a million by a million. Good luck with that one. Solve that first, then solve this one second. I challenge you today, if any group can tell me what the flow rates are through this pipe network, given the pipe data down here, if you can give it to me before 5 p.m., I'll give you a bonus 5% on your score. It's only 5%. Jose's like, forget that, man. That's not worth it. All right. Good luck, people. Like I say, I reiterate my desire. Find a partner. Start work on this today. You have an update, a progress report due on what, the 22nd? On that day, on the 22nd of November, I'm going to give you the big daddy, the king of pipe networks, and you're going to use your codes to solve that. So this here, the first one is a baby with 5 pipes. This is the toddler. How many pipes are here? 15? 1, 2, 3, 4, 5, 6, 7, 8, 14 pipes. So here we have 14 pipes with 14 unknowns. If we're going to use Newton-Raphson to solve this, we need to find the inverse of a 14 by 14 matrix in C. Have fun. That matrix is not symmetric. That does actually influence the outcome and is not diagonally dominant. So you can't use Jacobi to solve it. Bad luck there. On the 22nd of November, when you give me your progress report, I'm going to give you a network with 100 pipes. And you guys are then going to walk away, and between the 22nd of November and the 13th of December, you're going to use your codes to solve for that 100 pipe network. So your final report on the 13th will be showing me basically how you've used the GPU to compute flow through that 100 pipe network. That's your mission. So you've got a lot of work to do. May the force be with you. Find a partner and get cracking. And that's it for today. If you guys are going to continue mucking around with those make files for those GPU codes, I'm going to stick around and help you out. Otherwise, the afternoon is yours to do what you will. Good luck.